Okay, so we are at the bottom of page 3, and we're starting to talk about graphs of functions. So the first one we're going to graph is the function f of x equals root x plus 4. So first of all, since it's in a square root, we know that x plus 4 has to be greater than or equal to 0, because we can't have negatives inside a root. So that's why I'm setting the inside part greater than or equal to 0. And then if I subtract 4 from both sides, I get that x needs to be greater than or equal to negative 4. So the reason I'm doing this is because I need to plug numbers in for x to see what gets spit out for f of x. And remember, this one we used to call y, and now we're calling it f of x. So instead of x and y, we just have x and f of x. So doing this helps tell me what numbers I should plug in for x. So this says they have to be bigger than or equal to negative 4. So that means I can start at negative 4 and then see what that will give me. So if I plug in negative 4, I get inside negative 4 plus 4, which is 0, and then the square root of 0 is 0. So when I plug in negative 4 for x, it spits out 0 for f of x. And then we could keep going. I could plug in negative 3. If I plug in negative 3 inside here, I get negative 3 plus 4, which is 1, and then the square root of 1 is 1. And then let's think about what would happen if I plug in negative 2. Well, I'd get negative 2 plus 4, which is 2, and then I have the square root of 2. But that's not an easy number to plot. I don't want to plot the square root of 2, so I'm going to try to go up and find the next nice number. If I plug in negative 1, same thing will happen. I won't get a nice whole number, but if I plug in 0 for x, so I'm kind of skipping some, if I plug in 0 and add 4, I get 4, and then the square root of 4 is a nice whole number, it's 2. And then if I plug in 1 for x, I don't get a nice number. If I plug in 2 or 3 or 4, I won't get a nice perfect square under the root. But if I plug in 5, I get 5 plus 4, which is 9, and the square root of 9 is 3. And that's as far as I'm going to go. So sometimes you have to be, really thoughtful about the numbers that you plug in, because you want to try, if possible, to make them come out to be relatively nice numbers to plot. Either maybe whole numbers or halves, if possible. Now, remember that if you ever are graphing something, always label, meaning put x and y here, and then always put what scale you're using. And I need to go from negative 4 up to 5, so that's good. And then vertically, I'm not going very far, so I'm just going to go by ones. Put my scale in. And then I need to plot negative 4, 0, so that's 1, 2, 3, 4. That's right here. I need to plot negative 3, 1, which is here. 0, 2, which is here. And then 5, 3. So this one starts here. We know that x has to be greater than or equal to negative 4, so it has to start here, and then it's just going like this. And that's the graph this time. So you should always start by, if you're not sure what the graph is going to look like, you can always plot points. Later on in the semester, you will learn how to recognize right off the bat what the shape of the graph should look like but at this point we're just going to be plotting points. And then I'm going to write down here things that can help you graph. Obviously, a graphing calculator is very useful. And then a good website for graphing is Desmos.com. And then another site, a good math site, is WolframAlpha.com. So these maybe use after you've done work to check your answer. Don't use it to find your answer, use it to double check your work. Okay? Alright, let's do another example. So here we already have a graph filled in right here. Our graph, X, Y, and it has a scales. This says 5 right here. And then mine didn't copy really great, but it has a grid on here as well. And this graph is for the function f of x equals x over 3 cubed minus 1. So if you graphed this function by plotting a bunch of points, plugging in values for x and seeing what got spit out, eventually you would plot a graph that looked like this. So we're going to use the graph to find values for the function. So let's start with finding f of negative 3. Well, for this one, x is negative 3. So we need to find where that is. And so that's negative 1, negative 2, negative 3 is right there. And when x is negative 3, we want to see what the graph actually is, what the value of the graph is spitting out. Well, it looks like when we go to negative 3, the graph itself, f of x, is right here, and that is the number negative 2. This is the point negative 3, negative 2. So when x is negative 3, f of x is negative 2. So when you plug in negative 3, it spits out negative 2 for the graph. Okay, let's do another one. Find f of 0. So this time, x is 0. So when x is 0, that's right here, and then we look at where the graph actually is vertically, and the y value is negative 1. So f of 0 is negative 1. So this is the point 0, negative 1. And then part C, let's find f of 3. So we need to go to where x is equal to 3. So 1, 2, 3, and that's right here. So when x is 3, the y value vertically up and down is 0. So f of 3 equals 0. Because remember, y is the same thing as f of x. So we have the point 3, 0. So all the points are in the form x, comma, f of x. Another thing to notice about what we're discussing is that these are graphs of functions. And we talked earlier about relations and then the fact that functions are special types of relations, and we only want to graph functions. If a relation is not a function, we're not really concerned with that in this class. So, on the next page, we're going to discuss a test to see whether a graph is a function or not. It's called the vertical line test, and it states that if any vertical line intersects a graph more than once, then the graph and its corresponding relation are not functions. And the reason why this works is because if you have a vertical line intersecting a graph more than once, that means it would have more than one output, y value, for one input. And remember, for a function, we can only have exactly one output. So we cannot have more than one output like we would have here. So that's why if it doesn't pass the vertical line test, then it's not a function. So let's go ahead and apply the test to these graphs to decide if they're functions or not. So we just have to think about where any vertical line could be. So I could draw a vertical line right here. And this vertical line hits the graph more than once. And since that happens, it's not a function. The reason why is because, say we have this x value here. Well, this x value is being sent to this y value, and it's being sent to this y value down here. But we can't have that. Each x value can only be sent to one y value for a function. All right, part B. Now, no matter where we draw a vertical line, it's never going to hit the graph more than once. Each vertical line only hits the graph once. So this one is a function. Part C. If we draw a vertical line over here, that's fine. It doesn't hit it more than once. It doesn't hit it at all. But maybe here, we see, oh, it hits it twice, which is more than once, so it's not a function. And then part D looks a little bit weird, but this is the graph, and then also up here and going down is the graph. So we want to think no matter where we draw the vertical line, it can only hit at most once. So the only part of this graph that looks like it could cause a problem is right here, when x is -1. So does that vertical line hit the graph more than once? Well, that's all based off of whether the ends of the graph are closed circles, like this one, or open. So since this one is closed, the line hits here, and then as we continue down, since this one's open, it's not actually hitting the graph. If this one were closed as well, then it would hit twice. But since this one's closed and this one's open, it's not hitting it more than once, so we're good to go. This is a function. So let's go on to page 5. Now talking about the domain of a function. So the domain is the set of all inputs, usually values of x, for which the expression of a function is defined as a real number. So basically, it's the set of allowable inputs. So remember, now we're thinking of a function as f of x equals some expression. So sometimes there are certain numbers that you're not going to be allowed to plug in for x, so we have to leave those numbers out of the domain. So note, say we have a certain input and it results in an expression that is not a real number. We say that the function value does not exist, and that the input is not in the domain of the function. Let's do this example. Find f of 1 and f of 4 for the function f of x equals 1 over negative 4 plus x. Okay, so we've done this before. So f of 1 just means plug 1 in wherever we see an x. So we have 1 over negative 4 plus 1 equals 1 over negative 4 plus 1 is negative 3. So f of 1 turned out to be negative 1 over 3. So no issues happened there. Everything was fine. We plugged in 1. It spit out a regular number, negative 1/3. Now let's go on to f of 4. So we need to plug in 4 every time we see an x. So we have negative 4 plus 4. Therefore, in the denominator, we're getting a 0. Are we allowed to have zeros in the denominator of a fraction? We're not allowed. We cannot have 0 in a denominator. So, f of 4, we say, this is this node up here. This input, the input of 4, resulted in an expression that is not a real number, so we say that the function value does not exist. So I'm going to write f of 4 does not exist. And then note, this means that x equals 4 is not in the domain of the function f of x. Whereas over here, x equals 1, that didn't cause any issues, so this one is in the domain of f of x. Alright, let's do another one. H of x equals 7 plus root x minus 2. Okay. So this is our new function h, and we need to plug in negative 5, and we also need to plug in 4. So let's start with h of negative 5. So if we plug in negative 5, every time we see an x, we get 7 plus root negative 5 minus 2. And so we wind up with a negative 7 inside a square root. But we cannot have negative numbers inside even roots. We cannot have negative numbers inside even roots. So, h of negative 5 does not exist. And then let's find h of 4. So we have 7 plus root 4 minus 2. And this is 7 plus root 2. And so we didn't have that same issue this time. This is perfectly allowable. And then we always want to simplify as much as possible, but these are not like terms. We can't add 7 plus root 2 together, so we just leave this as our final answer. We can't go any further. So for this one, the number -5 is not in the domain of the function h, and then 4 is in the domain of that function. So the last two examples that we just did exemplify the two possible domain issues that we can come across. So in part A, the reason we had an issue is because of the denominator. We know that the number 0 is not allowed in a denominator. So that's the first possible domain issue, having a denominator of 0. And then in part B, the issue that we came across is this, that we cannot have negative numbers inside even roots. That's not allowed. So that's what I'm going to write here. The other issue is negative numbers within an even root. Okay, we cannot have these. So domain is a very big concept in this class. So this is something that you absolutely need to be able to, rattle off if you're ever asked, what are the possible domain issues we can have in a function? And you say, first, we can't have denominators of 0, and second, we can't have negative numbers within an even root. So make sure you definitely understand these two facts. And we're going to use these two facts to find domains of functions.